Namaste, students. In this session, we are going to discuss classical Doppler effect. Just like you saw in the short clip that I played, you saw how the sound of the siren, or the frequency or the pitch of a sound actually changes the moment when it uh, changes its mode. Like when it is approaching us with certain speed, it has a different pitch. The moment when it begins to recede from us, its pitch changes, or the apparent frequency changes, right? The one that is perceived by us. Why does it happen? We will understand. So as we can derive in a very intuitive manner, this is going to be very intuitive, and the derivation is going to be at the physical event level, right? Mostly at the physical event level, and we will understand what really happens at the physical level. Why does the frequency change? You might have guessed that I'm noting this as classical Doppler effect, right? The reason why I'm calling it classical, because the Doppler effect can also be, uh, you know, observed relativistically. Relativistic Doppler effect is also there, which is based on Einstein's spatial theory of relativity. And that would be a case where we are dealing with light or any electromagnetic wave that moves with the speed c, or anything, any speed which is comparable to c. That is, if I take any speed and divide that with c, with speed of light in vacuum is c, and the value we know, 3 times 10 to the power 8 approximately meter per second. Now that when that v by c is basically significant, actually we cannot say that is equal to zero, right? That will, when basically if v by c is not approximately equal to zero, we will say that we have to take into relativistic mechanics. That means their time in itself will not be the same for every frame of reference. That's one. Again, there is one more concept of relative velocity. Right, and that would be a little different, because when we take the relative velocity of light as per any frame, that remains c only, right? So first of all, let's discuss the concept of relative velocity, because that's going to be very important here. So relative velocity. Now we are going to discuss relative velocity in classical sense. That means if I have an object A that's moving with a speed va, velocity va, and there is another object B that is moving with a velocity vv, right? Both of them are vectors. Now what will happen if I want to find the velocity of A with respect to B? The velocity of A with respect to B will be velocity of A minus velocity of B, right? That means if A and B are both traveling in the same direction, the as for B, A will appear to be traveling at a speed less than actual speed V, right? But if they are traveling in opposite directions, then VV, if suppose VA is in this direction and VV is in this direction, right? So when I write VA minus VV or VAV, if I say that, that will be VA, which is positive if I'm taking the right hand side as the positive direction and the left hand side as the negative direction. It's going to be VA minus of minus VV, and that what happens, and VA plus VV. I simply have to add both the magnitudes. Actually, there is small here. I'm talking about the magnitude. So I will have to VA minus VV. So that will be VA plus VV. That will be the magnitude. Okay. I'm dealing with magnitudes only. So understood. So basically, when, let's suppose you are standing on ground and a car is approaching you. So let's suppose the car's actual velocity with respect to the ground is, let's suppose, 100 kilometers per hour, right? Now, if you start to move towards the car, let's suppose at 20 kilometer per hour, the car is traveling at 100 kilometer per hour. then to you, even if you are moving, to you, you are at rest, correct? So the car will appear to be moving at 120 kilometer per hour. But if imagine that you are moving forward with 20 meter per hour, 20 kilometer per hour, the car is also moving forward with 100 kilometer per hour, then to you, the car will appear to be moving forward with 80 kilometer per hour, right? So that's the concept of relative velocity. Now, before we again dive into the discussion of Doppler effect, we need to understand a few relations. We need to understand a few relations between the wave properties, right? Sorry, wave properties. And what are those? We know the wave speed v, the frequency of the wave, the wavelength, and the time period, correct? We know there are certain relations between them, like the wave speed is nothing but frequency into the wavelength. But that's one. Second, we know that frequency is simply 1 by time period or inverse of time period. Yes. So from that, we can say that the wavelength is equal to velocity, the speed of the wave by frequency, which is also speed into time period. Yes. So imagine that the perceived time period changes for the same speed, lambda will also change, right? And also, if lambda is held constant, but the relative speed of the wave changes, then the time period will also change. So this is something happens when we try to discuss Doppler effect. One more thing, for us to for us for our derivation to work, we have to assume a few other things also. Let's just discuss what are those quantities. First of all, you have a source. Let's say I denote my source like this. Right, this is a source, right? And there is my listener. I will have my ear here. So this is my observer, I will call it observer, right? The source would be moving whether towards the observer or away from the observer, it's up to you. But we will take only the derivation for the case where the source is moving towards the observer or the observer is moving towards the source. And then if the opposite case happens, all you have to do is to change the sign of the speed. So source moving towards the observer with respect to the medium. So all of it is happening inside a medium, right? So everything has to be measured with respect to the medium, right? In this case, velocity of the source or speed of the source, or let's call it velocity of the source also. Observer is basically moving towards the source with velocity of the observer, right? But we are taking Vs and Vo. We are not assigning negative signs because we are taking the case where both of them are approaching. If any of these, either the source or the observer moves in such a way that the separation between the source and observer is increasing, that means they are receding instead of approach. If the recession happens, then all you have to do is to, instead of Vs, you take minus Vs, instead of Vo, you take minus Vo, depending on what is the case. For the case that we are deriving, we are taking the sign convention that if the if the source and observer are approaching each other, then both Vs and Vo will be taken as positive. Now, medium, we don't have to assign a speed for the medium, because whatever is the speed of the medium, we have to find the value of Vs and Vo with respect to the medium, right? If medium has a certain speed with respect to the ground, and the source is moving with a speed with respect to the ground, then you have to find Vs will be basically Vsg minus v of the medium, or v velocity of the observer is velocity of the observer with respect to ground minus velocity of the medium, if medium velocity is given, if that is a concern. Otherwise, in most of the cases it will not be given, but if it is given, then you have to find the values depending on this. So the source observer can move towards the source or away from the source, and if it is towards the source, we simply call it VO, and if the source is moving towards the observer, it is Vs, right? Now, the wave that has been generated by the source, right? It moves with every wave has its own speed. Let's suppose that is V. Again, we take that the magnitude, the sign of this V, the speed of the wave speed. to be positive, it is moving towards the observer, right? Anyways, that would not be matter because wave move, so once it is created, the wave moves in all directions with the same speed in the same medium, spherically outward from the source. We have understood that already, right? So now this is our case. That these are the different velocities that we are dealing with. Okay, make a moment, take a moment to write this down. Understand. If you don't understand, listen to it again. Okay. All right. All the stages now set. Let's understand there are three cases that could happen, right? Let me put in a separator here. There are three cases that could happen, right? First thing is only S moving, right? That is one case. Second thing would be only O moving, and third will be only both S and O are moving. So let's discuss what happens when only S moving is the case, right? So here, this is case of only S moving. In this case, the observer is here on this side. The source is, let's suppose, here, right? And the source was here initially. Now the source has moved towards the observer. So what really happens? Look, the wave, as the wave that is moving towards the observer, starting from the source, and the source is also moving towards the observer, the wave gets stretched. You see here, the wave gets, sorry, compressed. You see, the wave gets compressed. Now, understand, if the opposite case happens, in case the observer is on the left and the source is now receding, the wave gets stretched, right? Wave gets stretched. So what happens? When the wave gets compressed, more number of cycles within in the same time period. But that means the frequency increases. More cycles, more frequency. When this, for example, take a spring, right? If you compress that, more number of turns happen in a specified space. So we can say for the same space corresponding to the same time period has more cycles, thus more frequency. If you stretch it, less number of turns, thus for the corresponding space, for this space corresponding to the same 1 second time, the number of turns or number of cycles decreases. So frequency decreases. That's exactly what happened in the video clip. As the siren started moving away from us, the frequency dropped, right? So, but the opposite case happens when the observer is moving. So in case of the only if only the source is moving, the actual wave gets stretched or compressed, depending on whether if it's compressed, if the observer, if the source is moving towards the observer, the wave gets compressed, right? And vice versa. But in case the observer is moving and the source is at rest, and nothing, so the wave itself is on unaltered, right? There is no change to the wave shape, right? The wavelength remains the same, no stretching, no compression happens. But since the observer is approaching, the wave is coming towards the observer with V, and observer is approaching the wave with VO. In this case, the observer will consume the entire wavelength faster than what he would have taken had it been at rest, right? Now, if the observer is moving away from the source, then it will take him longer to consume the same wavelength, right? So basically, if the observer consumes the wavelength in the time period only, then he will be perceiving the actual frequency. But if the time period that the observer takes to consume the wave decreases, then the frequency appears to be increasing. And if the time period gets increased, then the observer will basically will say that the frequency is less, right? So basically, this is what happens is the end for the entire wavelength, the observer, or let's suppose I'm taking this entire wavelength starting from here to here, right? This wavelength, this particular wavelength, if the observer is at rest, will take the time period t. But if the wave is already moving towards the observer, but the observer is moving towards the wave also, then the time period that the observer requires to consume the entire wavelength will be less. And vice versa. If the opposite happens, the opposite case happens when the observer is trying to move away from the source. Now, let's discuss only S moving, right? In this case, what really happens? Let's see. Let me draw two vertical bars, one here and then one here. And let me, in this case, fix this to the ground. That's my observer O. But this is my source S, right? Yes. Now understand. The we are saying, let's suppose there is a wave of there is a wave that is about right. There is a wave which is about to be created, which is about to be created, and let's say this is the wavelength, right? The the distance between these two ends is simply lambda, correct? Now, if this is the case, let's see. I am bringing it here. Understand this wave, right? Let me delete this one. Let me delete this one also. Let me delete this one. Just look at the wave. It's about to come out of our. It is about to come out of our. Let me see if I can delete this one. Okay. This particular wave in green is about to come out of the source, right? Now, let's suppose we started the timer now. The source is turned on, right now. The wave starts to move towards the observer now. Gradually, the entire wave will be coming out of the source. Yes. So by the time the wave has come here, right, the source will not be at rest. The source would have also moved forward, correct? The source would have already moved forward by a certain distance. Let's say the source has now come forward by this distance. This distance. Yes. Now this is the new position for our source. The source has moved through a certain distance, and because why? The source is moving with a speed vs with respect to the medium, correct? So now what really happens to source? So actually instead of having looking like this, the source would now appear to be moving like somewhere like this. It will be a little distorted, right? Basically it will be a little distorted like this. So now this is the apparent wavelength of the wave. The actual wavelength was like this. The actual wavelength was like this. From green to green, that was the actual. That was lambda. But here, the apparent wavelength here will be lambda dash. What is lambda dash? Between these 2 points, it is simply lambda minus this distance that has been moved by the source. So basically, how much time does it require for the source to generate one complete wave, starting from here to here? This entire wave requires a time period t for the source. That's the time period of the wave. In the same time period, the source has moved forward with the velocity vs. So now we know this red part. The red part, this distance is nothing but Vs into T. So lambda dash is lambda minus Vs into T, correct? Now let's get back. Here, that's it, done. So basically for the observer who is at rest, he will perceive a deformed wave which has a lesser wavelength, right? So for him, lambda dash, which apparent wavelength that the observer observes, is the actual wavelength minus Vs into T. That also means now lambda dash is what we have discussed in the wave properties section. Lambda is V into T. So lambda dash will be V into T dash, right? That means lambda dash will be V into T dash. Apparent time period will be the actual time period lambda, which is V into T, right? Because the speed of the wave is not changing, minus Vs into T. From this, we can simply say that T dash is equal to the V goes to the right hand side. It is simply V minus Vs divided by v into time period, correct? Now, I also know that the time period is inverse of frequency. I can also say frequency is inverse of time period, right, from this equation. So I can say that time period is inverse of frequency. So I can write 1 by frequency apparent f dash is v minus vs by v multiplied by 1 by actual frequency. So let me just flip the equation upside down. So f dash will be f into v divided by v minus vs, right? That's my equation 1. Okay. Here, if the source, instead of approaching the observer, recedes from the observer, instead of v minus vs, you will put just plus vs. Okay. That's all. Now, second case. Let's separate again, create a new section. In the second case, we are going to discuss what happens if only observer is moving. If that happens, now understand the source. I will draw the same thing again. If can I copy? No, that will take more time. Let me draw again two lines here, right? One for source and one for observer, right? Imagine, first of all, let me fix the source here because the source is at rest. And let's suppose this is my source and this is source and this is my observer with an ear here. This is my observer, correct? But the observer is moving towards the source with a speed VO, and that is only VO if it is approaching the source. Otherwise, if it is if it is moving away from source, I will put minus VO. But our sign convention says approach. The signs that we are using for the derivation are only for approach. The signs will be opposite for the respective cases if they are receding. Now, understand. Let's imagine that the source is at rest. Now, a wave has been generated like this, right? A source has been generated like this, and I join these two lines. So basically, this is the true wavelength of the source of the wave, and the wave is not. If the wave is moving with a speed v, right? Wave speed with respect to the medium, right? Now imagine if for a second, if the observer does not move, then the entire wave, right? The entire wave to pass through him to get inside his ear, the entire wave to pass through his ear like this, right? The entire wave to pass through his ear or to be consumed by the observer at rest, how much time will it take? T seconds. The time period of a wave, the entire wave will basically get through the ear of the observer, right? But the observer is actually moving with VO. That means the observer here, in some, let's suppose, for as the wave tries to pass through the observer's ear, observer is also trying to cover the wave in the opposite direction, right? So basically, to the observer, the wave v of the wave with respect to the observer will be equal to v plus vo. Yes, that will be the apparent speed of the wave with respect to the observer. So how much time will it take for the same wavelength lambda? The time that would take the observer t dash will be wavelength divided by the speed of the wave with respect to the observer, v plus vu. That's it, right? This is the time period that will take. See, imagine that if for example there is a long train, right? If the train, you are standing at a particular place, if the train moves across you, then for the train, if you're standing here, the train to totally cross, how much time will require? It will require whatever the speed of the train is divided by the length of the train. Sorry, the length of the train divided by the speed of the train. So length by speed, right? But imagine the same train is basically trying to cross you while you are also moving with your speed. Let's suppose vu, right? So this is v, this is vu. So how much time? T dash will be the length of the train divided by v plus vu, because the rate at which the length of the train is decreasing, that is basically an enhanced rate. That's the speed of the train as well as your speed. And since both of you are moving in opposite direction, you will be crossing the train faster than before. Right? The same thing is happening here. Right? So T dash is lambda by V plus VO. Now done everything. T dash is lambda divided by V plus VO. Hence, T dash is equal to lambda. We know lambda is V T speed into the actual time period divided by V plus VO. That means it's simple. T dash, I will say T dash will be 1 by apparent frequency dash, then 1 by F dash. That is V by V plus VO. And the time period here will be 1 by F. All I have to do is to flip the equation. So I will simply write my equation as F dash is equal to F into V plus VO by V. And that is my equation number 2. Got it? Now what happens if both of them are moving, right? Let's again discuss the last case. Third case, right? Which is pretty easy actually. Third, if both S and O, source and observer, are moving. Now, in this case, we will discuss again the approach case. In the case of recession, you will simply have to flip the signs. Okay. Okay. First of all, we will have an apparent. Let's imagine we take first the apparent frequency due to source's motion, and then whatever apparent frequency we get, that will be, again we will take the apparent of the apparent when this observer's motion is counted. So apparent frequency due to source's motion is equal to true frequency f, right? And that we have taken equation 1, which is f into v divided by v minus vs. So this is v divided by v minus vs. Yes, but the apparent frequency, the final apparent frequency, which is the apparent frequency of the frequency due to source's motion apparent to the observer. Now, I'm including the observer's motion also. Instead of f dash s, I'm writing f dash so. That is, so now what I'll do, I'll put some value for the frequency, right? And then divided by v plus vo by v, right? In just above v plus vo by v. But here I have to put in the apparent frequency due to source's motion, right? That is f dash s. So that becomes, we have gotten this value on the top. So apparent frequency will be f into v by v minus vs multiplied by this factor, which is v plus vo divided by v. So it's pretty simple and clear cut that f dash for combined motion will be simply f into v plus vo divided by v minus vs, which is the, actually I would say, is the only formula that you need to remember after understanding, of course. So in this case, plus in the denominator and minus in the plus in the numerator and minus the denominator happens for approach case. But again, negative, this plus will be negative divided by positive will happen for recession. So choose accordingly. And all these speeds are with respect to the medium. If the medium itself has a speed or the velocity, then find the new values. Okay. For the speed of the wave with respect to the medium, VO with respect to medium, VS with respect to the medium. Right. So that's the formula. I hope you've understood. If you have any doubts, you can connect with me at thephysicist.in/ask. That's for you. Just register using your Google account or Gmail account and then start asking questions. All right. So see you in the next one. Till then, goodbye.